coming out. We are Team Injection Perfection. We're in the second semester. We're going to present to you our finished product and what it took to get there this semester. The way it's going to go is we're going to discuss what we did each individual as we lay out on the screen there. I think we'll open it up to questioning after that, and then we would like to show you our machine out here in the plastics lab. So that's the order of the presentation. I'm going to go first, and first thing I'm going to talk about, I call Brad's Senior Project Top 5. These are top 5 things I learned about Senior Project. The first thing is, there is a reason that machining is expensive. Tooling is expensive, especially when you break it, and you have to buy additional. Sometimes a setup takes longer than it takes to run the part, oftentimes. There's a lot of expense that goes into upkeeping files and camming and softwares. And so there is a reason why it costs a lot of money. The second thing I learned is in computer automated manufacturing, the post is everything. Okay, you can do all this fancy work on camming software or when you draw it in CAD, but if you don't communicate with the machine correctly, it's not going to work. So, the third thing I learned was designing mating parts is hard. It is difficult to figure out tolerance and figure out how two parts are going to fit together, especially when you're not the only one designing it, when you're trying to make it mate with something somebody else designed. It is extremely difficult. And anybody that can do it right the first time, I'll pay money to mentor with that person, because I would like to figure it out.
That person doesn't exist.
Takes 3 times.
There will, yeah, and that what brings me to my fourth thing is there's always going to be changes. Your first design, if that's your end product, your first design, that's another person I would like to be my mentor. I would pay money for that, because there's always going to be changes. And the last thing I learned, it was something from Carrie. Carrie came up with this. Brad is not only a noun for a name for a person, but it's also a verb. It's the act of making a mistake on Senior Project. Carrie would go around asking if you did a Brad today. So, it was difficult. Okay, so on top of being the project leader and trying to help everybody with their projects and what they needed, I also built a few parts on my own. And this is where some of my lessons came in machining and computer-aided manufacturing. The first part I worked on first major part I worked on a few parts that were small, but this one was our nut that holds our threaded rod in, and you'll see that when we go look at the machine. And I'm going to tell you the truth, this part took me 3 weeks to build. It really did. I had a rough time. I had a problem with the post. I broke countless 1/4-inch carbide end mills, and I just had a rough time. But the good thing about that is I took the lessons I learned from this part, and on the next part that I programmed, I got some consulting from George, and he really helped me out on this, and I really appreciate that. And like I said, I took the lessons I learned from that one, and I cut my 3-week build time on that one down to about a week on that one. So, good to know I can learn something. The other thing I worked on is I worked on our sheet metal parts, and I cut them out on the Mata punch press. And this went significantly better. There were a few issues, but it went really well. That was my flat pattern for those, and this is what the end product on the model looked like for those parts, and you'll see those on the machine. One thing I neglected to mention, I'd like to say, is I'd really like to thank a a lot of people that helped us out on this project. Carrie helped us out with some of the manual machining. George consulted and helped us out on a lot of the CNC. Jasmine helped us out on the laser, and I really thank you guys, all of you. Thank you for your help. I'd like to turn the time over to Joe.
Thanks, Brad. I'd like to say thank you also. It's been a good semester. Happy to be done, hopefully. What I did coming into the semester was mainly reviewing the schedule, trying to keep us on track, and I didn't have many other responsibilities other than make sure we were on track and actually building a lot of the parts. Most of my time was spent on the shop floor producing the parts, and we're very happy to have a finished, completed, and working model out here for you today. It's going to be a nice thing. We're very excited to say that we met our deadlines. We didn't spend many days. I think we had 3 days where we stayed past 3 o'clock working on parts and trying to assemble it. So overall, we stayed on track very well. We did have a few delays though, and that was probably my main thing that I learned, was trying to work around schedule. You have to be adaptive, you have to be able to change as the process goes along, because like Brad said, we had a part that took 3 weeks. You remember what you said, how long it was going to take you when I first asked you how long?
Yeah, probably a couple days.
So that was kind of a big hit. It made us work a little bit, but we adapted and changed. Another thing that kind of slowed us down was we were trying to stay within our budget. Didn't have much money to work with. We had a lot of donated material, or we got a lot of material out of scrap bins. So we ended up doing a lot of extra processing, trying to stay under budget, which cost us a little bit of time. And this was actually just one day that I spent out in the mill just facing some material to run the CNC to make a couple brackets, and that's everything, all the shavings from it. And then like last semester, and it's kind of already been addressed, we had our Brad, we called it B Factor last semester. Most people know about it now. It was a little bit different. We weren't as concerned for his safety this semester, but yeah, he did learn a lot, and he did make a few mistakes, but it was all good for the learning process. Did someone say something? One other thing that we tried to do was make our parts interchangeable, make them consistent, stay within our tolerances. We have a few welded sub-assemblies in this project, and so we did actually do a little bit of fixturing so that we can keep everything accurate as we're trying to line up the barrel and the plunger. That's very important. So we built some fixturing for when we went through and welded, and everything turned out very well. It worked to our advantage, and it helped us improve our quality and reduce the amount of time that we spent reworking. And I say thank you and turn the time over to Jake.
I'm Jacob Bailey. My job in this project was a quality planner. For the first thing that I did was to kind of make a sign-off sheet for all the parts that we were going to make. And this is what we had hanging up on our shop wall. And it's kind of a flow chart of all the parts that we need to make. And it first starts off with all the parts and the part numbers. And the first thing here is a release date from me. All parts that get manufactured in the shop I have to see the print, and I have to sign off every sheet so that it can be passed off to say it's okay to be built. The next section here is the stock cut size, or the raw material, from the part being released, meaning that you can take that the drawing and go and either go in the shop closet where the stock material is to find that material, or if it needs to be purchased. And once that is cut, it's signed, and that is placed on the side to let the next person, whoever is going to build the part, know that it's ready to be machined. And once you start building a project, the person needs to sign a date saying that that project or that part is being made, so that other people don't make the same part, so we don't have any problems with, you know, 7 parts of this and 1 part not being made. And then once the part is complete, the person signs it saying this part's complete and it's okay, ready to be inspected. And that's the final thing there is the inspection. And once it's inspected, it gets signed off and it means that part's completed. Another thing that I was in charge of was kind of the shop layout, how things were going to be run in the shop. In our little senior project area over there, we had some tables there, and the first table we had there was the raw material table. Pretty much that's when we cut the material, the plan and the material stay on that table, saying to whoever is going to build the part that this part's ready to be made. And then once the part is machined and completed, it goes to a center table where that table is the inspection table. All parts go there to be inspected by Tristan and Michelle. And then once the inspection is complete and the part passes, it goes to a third area where it's ready to be assembled. And from that table it gets assembled into our final project. Some of the processes that we had in the machine shop were the manual lathe, which I mainly ran the manual lathe. A lot of the parts were done by me on that. The manual mills were pretty much run by Brad and Joe, cutting those parts. The CNC lathe, I ran the nozzles on that. That was a little tricky on my part. I learned that 4140 material is a little tricky to machine. A lot of times it seems like it wants to, take off a lot of material for it to machine well. And also the speeds and feeds are a big thing when machining 4140. When I was machining it the first time, a lot of times it would come off centered as I was machining it and get all bent. I was having the hardest time trying to figure out what was going on. Through adjusting the manual speed and feeds and depths of cut, I finally got the part to work. The CNC Haas was ran by Joe, doing some of the brackets. Like Brett mentioned, he did the CNC Mazak and the Ridgeport for running some other parts. And Brad also ran the Amada punch on the sheet metal parts. And Michelle ran the laser to do our acrylic shields. And now I'm turning the time over to Michelle.
My name is Michelle Hendon, and my job for this project was documentation. And this included, as it says here, keeping the manufacturing parts aligned with the prints that were created in the first semester. And so doing that, I used inspection sheets, which I'll show you on the next slide, so that each of the parts, as they were built and finished, they were inspected to see if they were under tolerance. And then also I needed to keep the design updated with the changes in the manufacturing process. As we went from where we started last semester to what it is now, there's been a lot of changes made on this machine. And we've had to keep it updated with engineering change orders so that we can keep track of those changes. And also, as the semester progressed, we added a lot of new parts as we enhanced the design. Okay, this is the inspection sheet that we used. It was just a blank sheet of paper that was filled out for each and every part as they came through, so that we could check the tolerances and make sure that they're accurate. These are the tolerances that most of the parts followed. Last semester we had done a lot of tolerances, and the faculty said that many of them were too tight and we wouldn't be able to produce them. So we followed general tolerancing, which most of them had 10 thousandths of an inch tolerances, and we found that it was a generalization now instead of too specific. Many parts, as it says here, were out of tolerance, but they still worked in the assembly, and they mated with the other parts. So we learned that it's important to learn how to design for manufacturing and how the design was going to be put together. So that's an important thing we learned this semester. These are the engineering change order sheets, and we filled out quite a few of these. We were kind of surprised. Carrie wanted to know specifics, and out of 52 drawings, we had 21 change orders, which is about, 45%, close to 50. Quite a few. And the reasons for these changes were varied. The first one listed is the available material. Like was mentioned earlier, we had a lot of material donated, and so as an example, in the frame, we had designed a 2-hole angle, and when we wanted to look for the hardware, all we could find were 3-hole angles. So we had to change the design to match the material that we had. And then there was also assembly mates and clearances that were a problem, especially as we started mating parts and realized that they didn't go together. We needed to make changes. Additional parts, like I mentioned, and the part material and size. As an example, there were rod bearings that were made out of UHMW, and we decided to change it to nylon so that it would work better. And like Brad, I realized in this project and in this field, as I've been working and going to school, that there is always changes, always. These are the additional parts to the design that we added. Listed here, the right side and left side plate, as we distinguished between the two when we added the cabin system. The funnel, as Tristan Will mentioned in his part of the presentation, a thermostat standoff, a plunger guide, and cheetah bar. Because earlier we had a full lever, so we didn't want 2 parts. We decided to cut the lever in half and add a cheetah bar. And also the plunger guide, it was really quite interesting. We added the plunger, and as we brought it up out of the barrel, it was really wobbly. So we needed a bigger guide so that it would stay aligned as it was worked. We also eliminated many parts which required ACOs. And besides keeping track of the design and the inspection of parts, they let me make a part, and it was quite fun. I worked with Jasmine Harris on the laser, producing the code shields, and she helped me set up the files to profile the dimensions and cut the holes, and also to engrave this image, which you'll be able to see when you see the machine. Anyway.
My name is Tristan Sadler. I was the treasurer for the injection Perfection-2. So one of my jobs was accounting for the money that we spent. Last semester we spent $50 on the bench test, and then this semester, with a few of the parts that we bought, we spent $285.57. And it's important to track the money throughout the process of your project. Also, it's important to keep in mind from the beginning of where you want to be at in the end. So you don't spend it all up front in the end. And we were smart and we used a lot of the material from here at Weber State, so that saved us a lot of money. So as you can see here, the redesign of the funnel. This is the final product, which is the plunger. You can see the barrel here, and then this is the funnel. Last semester we proposed this idea of making a hopper that's made of plastic. And one of the things we ran into was the angle from here to here. We were worried about it getting jammed in there and stuck, and that got brought up. And this is one of our very beginning ideas of the funnel and how we wanted that to work. In the end, we went with the product that we purchased, and it could be replaced. And so this is like a mug that has the threads on it, and we just cut it. it threads right onto the barrel. Thank you. So that's the way that went. So we just totally went away with the hardware system. And like I said, we purchased that. Most of my time was spent on inspecting the parts that were machined. And the steps I learned in that, I thought back to my Bob Milner class, and he taught us how to inspect parts and to be accurate, to have a clean surface when you put the part down, so you can have there's no dirt there, nothing interfering with your inspection. And then using the correct tools for the job. Some of our parts, our cheater bar, were close to 3 feet long, so we use the long calipers to inspect those. And then, if it doesn't work inspecting something one way, just try something else. You've got to be creative or ask someone that already knows. Helped out with the project binder, keeping it organized and putting it together. This was important to help the whole flow of the entire project. Another thing that we all learned was working within a group of great people. The word synergy, it means 2 or more agents working together to produce a result not obtainable by any of the agents independently. And we had fun working together on this project, setting goals as a group and accomplishing those goals, working hard together to create a great product. And of course, project management and the ongoing development of the project, so that we can have a nice final project, and of course making friends throughout the entire process. Turn the time back over to Brad or have questions.
Yeah, again, thanks everybody that helped us out on this project, and like I said, this is the time that we want to open up to you for any questions that you have for any of us.
I don't have any questions. I just was looking through all of your documentation and the way you have your drawings and marked up drawings and operation sheets and cost estimates and all that stuff. I think that's fantastic.
Well, that's on Michelle.
I think, but I mean, I saw everybody's hand in it though. I could see your name on the drawing is drawn by, her name on the drawing is checked by, Joe's name on some things down in the revision block, things like that. I think that the process, you kind of alluded to the fact that design is an iterative process, and getting it right the first time is a very difficult thing to try and do. I just think that's very well reflected in what you've compiled here. I think it's very good. The drawings look really pretty good.
Thank you.
So I think it's a lot of really good hard work. I see a very conscientious effort on the part of the team to make sure that you followed through. There's so many times that you make the first set of drawings and then let's just set up to the side and you build it the way that you end up building it, and sometimes you never go back and get that cleaned up. But it looks like you guys made a very conscientious effort to go back and make sure that the documentation was correct. So I think it looks really good. Sorry I didn't let you guys take a look at it. I just had so much fun.
I'll follow that up with a question, because my interpretation of what I saw in glancing through it was that it's still in process, that it isn't complete. There were so many drawings that were marked up. Maybe I don't know if I saw the final set, or because when I was looking through there I saw a lot of drawings that were used as shop drawings, and so there's a lot of editing on the drawings, red lines, yellow marks, pencil scratches, the drawings that were used out in the shop for production. Could you explain what that?
Yeah, that section of the binder is the release drawings. That's what Jacob released as it went onto the shop floor, and changes were made on those drawings, and then those changes were put on the drawings.
So the final released drawings are in the other binder?
Yeah, it looked like the small binder had what you're talking
Yeah, we had
about,
to go to two
and then
binders
the
to
big
do too much
big
stuff.
binder was the finished, because there was a finish, looked like a cleaned up, completed drawing,
Yeah.
the first section of every, or the first drawing in every section.
I wanted to them to archive what they had done so that you could see the progression of how things work. One of the options would be to throw away everything that was that was done last semester and to just show what was finished, and that's not what they spent so much time with, and so that was one of the reasons why you had that in there,
You kept
to
those,
see the,
working drawings.
Yeah.
I
Yeah.
guess I'd be a little bit cautious about marking those as being obsolete or something, so they're not then used if anybody wanted to follow up with
Put a
this.
big red stamp on it.
Yes.
It's
Yeah.
obsolete or something.
Mark
Jeremy,
them
did you have a
obsolete.
question?
More of a comment that I think that for me, I'm going to be showing this video now, especially with your comments, Brad, if I ever teach 1060 again. Because that is one of the hardest things. I think students come into the program thinking that this is a magical scenario where we sit down and we design some assembly and it's just magically going to fit together. And then, Meg has the audacious task